the previous lecture, I motivated the wave motion and showed you that if I have a continuous medium, right, a string or air in a pipe or the sound traveling in free medium, the equation of motion satisfied was d2f by dt square equals 1 over v square d2f by dx square, again emphasizing that I am actually doing a one dimensional motion, and the solution is f t plus or minus x over v, where plus sign means wave traveling in negative x direction and minus sign means wave traveling in positive x direction. And then I showed at the end of the lecture that if instead I have discrete masses, then I cannot write the second derivative with respect to x, and wrote the equation as d2f by dt square, and now f will be at sth site. So, let us call this sth site, this is s minus 1, s plus 1 and so on is equal to constant f s plus 1 plus f s minus 1 minus 2 f s. This is what I had just intuitively said should be the equation. Now, actually I am going to show you that this is the equation when you have these discrete sites. So, let us assume a one dimensional crystal where I have these atoms arranged along, let us say, the x axis with connected by spring, right, so with some spring constant c. Mass of each atom is m, they are all identical atoms, and I disturb one of the atoms either longitudinally or transverse. So, I can have two kinds of motions for this. If my atoms get displaced perpendicular to the length and the displacement obviously then travels along the length, it is transverse, or I could have a displacement of these atoms along the length, this will be called longitudinal. And right away I will tell you that if I have a transverse motion, it has 2 degrees of freedom. Why? Because as I showed in this blue thing out here, right, let me use a different color for the transverse motion. The motion could be along the plane of this screen or perpendicular to it. So, there are 2 degrees of freedom. Longitudinal, however, has 1 degree of freedom only. That is along the length of the string. Let us see what is the equation of motion of this string is going to be. So, let me make this string again. Here is an atom, and I am going to assume, okay, we will generalize it later. Right now I will assume for simplicity each atom interacts with its immediate neighbor. That is, if I have an atom at S, so let me make this string again. An atom at S site will interact only with S minus 1 and S plus 1, no others. In general, there could be and there will be interaction with other atoms also, but right now for simplicity I am not taking that. You could also assume that the only force which is large enough to be taken into consideration is that with the neighboring atoms, others are very small, but one can generalize it, which we will do later. Right now just focus on the idea. Now let this atom be displaced by a distance Fs. Okay, so it has a new position Fs. Let the next one be displaced by Fs plus 1. This is displaced by Fs plus 1, and let the previous one be displaced by Fs minus 1, so that the distances between these atoms change. They change from the equilibrium distance, which was A, right, let me use a different color, which was A, to slightly different, and I am assuming a force proportional to the displacement, that is spring like force, right. So, that assumption number 1 was that each atom interacts with its immediate neighbor. Assumption 2, force is proportional to displacement. In fact, I readied you for this because I was kept making these springs between the atoms. So, it is like a spring between these atoms, and force is proportional to displacement. Let us see the directions of these forces and how the force on SS atom looks like. So, let me make this figure again. Here are these atoms connected by springs, and only neighboring atoms are applying forces on each other. This was the Sth atom, this is S plus 1 atom, and the interaction is only with the neighboring atoms. This fellow has been displaced by Fs, this fellow has been displaced by Fs plus 1, and this fellow, the last one, the previous one, has been displaced by Fs minus 1. Now, force on the Ss atom, this atom, right, the Ss atom, force on the Sth atom. There will be force due to the atom on the right and the force due to atom on the left. So, this will be equal to sum of the forces due to atoms at S minus 1 and S plus 1, assuming only neighboring atoms apply the forces. Now, what about the force due to S minus 1? So, let us calculate force S minus 1. I am just labeling it S minus 1. It is going to be proportional to Fs minus Fs minus 1, and you may want to subtract A, all right, and there is some constant. Let us see if the direction is right. If Fs minus 1 minus A is positive, that means the spring is stretched, then the force on the Sth atom, if the spring is stretched, will be to the left. A string, stretch the spring, will pull it in. So, I should put a minus sign here. Now, let us write the force due to S plus 1. This would be equal to f s plus 1 minus f s minus a times c. Let us see again what the direction would be. If f s minus 1 minus f s minus a is positive, that means this is stretched, right, then again the spring will try to go back to its original position, and therefore, it will pull this sth atom to the right. So, this direction is correct. Now, let us add the two and see what the net force is. So, net force will be the sum of these two, and what do you get? You get C f s plus 1 plus f s minus 1 minus 2 f s. Net force is the sum of these two. I have added these two, and this is the force we get. So, let us see what we have got. We have this one dimensional crystal with each atom with mass m, and we have found that the force on sth atom, and let me write it again, assuming interaction with immediate neighboring atoms and a spring like force. This is the assumption, right. Then the force on the sth atom came out to be some constant, spring constant C times f s plus 1 plus f s minus 1 minus 2 f s, and therefore, the equation of motion for the sth atom will be mass of the atom d2 f s by dt square is equal to C times f s plus 1 plus f s minus 1 minus 2 f s. Let me box it. And pause for a moment to give you time to go back to the previous lecture and see that when we took the wave equation for the continuous medium for a string or air or whatever and discretized it, just intuitively it gave us exactly the same equation. So, the equation of motion for this sth atom is this, which is discretized form of the wave equation, right. So, let us write this again. I will keep making this to emphasize that what we are considering. So, the sth atom satisfies the equation is d2 f s by dt square is equal to C over m, I have brought the m to the other side, f s plus 1 plus f s minus 1 minus 2 f s. And let me just to make the point again, it is discrete form of the wave equation. This is the equation of motion. If this is a discrete form of the wave equation, I should expect similar solution for a given frequency omega, right. So, we will now try that. So, this is assuming that atoms interact with only the neighboring atoms and the force is spring like, with C being the spring constant, we have found the equation of motion for the sth particle, which is of the form given here, which is the discrete form of the wave equation. So, expectation is for the solution will be a wave-like solution. In particular, if I am looking for a solution with a particular frequency, it should be like sine omega t minus k x, except that x is not continuous anymore, right. So, let me write this again. I will just focus on the wave equation now. So, I am looking for d 2 f s by dt square is equal to c over m. I am looking for the solution f s plus 1 plus f s minus 1 minus 2 f s, and I am looking for harmonic solution, that is solution with a given frequency, and let me also specify that frequency to be omega. Then the solution f s t, this is at the sth site, should be some amplitude, right, some amplitude, let us call it a, sine of omega t minus k, and instead of x now I have to put that discrete variable s times a, right. So, x has been replaced by S A, that is the distance of the sth atom from the origin, which I will call s equal to 0. So, hopefully by now I have brought you to a point where you understand that in a discrete lattice, in a discrete crystal where atoms are a distance a away from each other and connected by springs and are interacting only with the nearest neighbors, the equation of motion for an atom at sth site is exactly like the wave equation, except that now we are writing that second derivative in discrete form, and therefore, the solution would also be wave like. In particular, if I am looking for solution with a particular frequency omega, that is a harmonic solution, it will have the form sine omega t minus k s a. And with this now I can find the relationship between omega and k. We will find this solution in the next lecture and discuss its properties.